I have some good news for you. This is our last lesson for Unit 4, which means it's actually our last vectors lesson, like in total. That means that we're halfway through the course, guys. So calculus is right around the corner. We have to make sure that this last video is epic. Okay, so we're going to do lesson 4.5, the intersection of not two planes but three planes. What I have here are 8 different cases, that's right, 8 cases of how three planes will touch. Okay, so we're going to go through them, and the math itself, like the process, is very similar to the intersection of two planes. We just have more cases, that's all. Let's go through them, and then we can get through some examples. So I have 3 plane formulas in scalar, and that's basically what the questions will look like. Like they'll be like, okay, here are 3 equations, find the intersection of all 3. What I've done is I've grouped 1, 2, and 3, so case 1, case 2, and case 3 together, but I can only fit 2 on the screen at the same time. So you'll see case 3 at the bottom, and we'll get into that one in a second. I grouped these 3 together away from the other 5 because I felt like they had something in common. Okay, now no matter what example you're given, the very first thing you're going to do is try to find the normals. You guys know how to do that now. So the normal vectors are your A, B, and your C. So this one right here is going to be the normal vector for the red. These guys here are going to be the normal vector for the green. And if they're scalar multiples to each other, it means that both of those planes are parallel. Okay, now this is the unique case, well, sort of unique case, I'll tell you why it's unique in a second, where you have 3 of the normals all scalar multiple to each other. Okay, that means that all 3 planes are parallel to each other. But you can take a look at case number 2 and say, well, actually, all of those ones are also parallel to each other, but it looks very different than case number 1. So what I'm going to do is I'm just going to say, okay, in both cases, by taking a look at the normal vectors and saying that they're scalar multiples, we can then say all 3 of the planes are parallel. But to distinguish both of them from each other, like case 1 and case 2, you want to look at next their d values. If I'm going to compare this guy to this guy, I'm going to say, okay, if the red A was doubled to get the green, and this red B was doubled to get the green, and then so on was doubled, if the d's are also doubled, it means the entire red equation was doubled to give you the green equation. That must mean that they're coincident. Okay, as in they're the same plane. Number 1 I was saying before is unique because we have all A, B, C, and D, so all of the normals and all of the D values are scalar multiples. This is the only case that shows that because this case, all 3 of the planes are coincident. When you take a look at the solutions now, the solutions means where do all 3 of the planes touch? What points exist on all 3 at the same time? If you take a look at this section just right here, but visualize that these planes can get bigger and bigger and longer forever. Okay, right now in this diagram, this is where all 3 planes touch. So this touches the bottom, which touches the next one in this specific section. That means that your answer will look like a plane. Okay, as in all of your infinite number of solutions are in the form of a plane. Your answer then, if you were to go through the entire process, like all of the math, you should get an answer that looks like ax plus by plus cz plus d equals to 0, like the equation of a plane. So your answer should not be a point of intersection. Do you get what I'm saying? Okay, now let's take a look at case 2. Well, case 2, if you take a look at the d values, they're actually not all scalar multiples of each other. Only 2 and 3 are. And that makes sense because 2 and 3 planes are coincident to each other, whereas plane 1 is distinct. And that means that you'll see the scalar multiple is actually not existent for plane 1 compared to both of the other planes. Okay? In this case, you actually don't have any solutions because there are no points that exist on all 3 planes at the same time. Let's check out that third case now. So like I said, I had grouped it together with the other two because when I take a look at all of the normals, all three planes are parallel to each other. But this guy is different because none of the planes are actually coincident, and I can see that through comparing the d values. So these three cases don't require like a lot of math. They just require two checks, and then you're pretty much good. Okay, now in terms of the solutions for this last case, there are none, again, because none of the planes have points that exist on all three planes at the same time. Okay, let's get into case 4 and case 5. I've grouped these two together because they kind of look similar to me as well. I can see in both cases in the diagrams, there's two planes that are parallel, whether they're parallel and distinct or they're parallel and coincident, but then they have another plane that are not parallel to them. And so I can see that when I start to look at their normals. They have normals where maybe one set equals to each other, but the other set does not. Okay, so you can see that plane 2 and plane 3 are parallel. That means that their normals should be scalar multiples. But when you take a look at that last plane, the scalar multiple will not be there. Okay, now that does also exist here where you have two planes that are also parallel, and you can see that right here. But then this plane is not parallel, and so you don't see a scalar multiple. And I mean, like, that makes it difficult to really distinguish between the two cases. How do you know when you have case 4 and how do you know when you have case 5? Well, you can start to look for your d values because in this case, two of the d values should be the same, but the last d value should not be a scalar. And that means that two of your planes are actually coincident, which does not exist in the case 4. So in case 4, you shouldn't actually see any of the d values equal to each other. Okay. Another way that you can distinguish between the two cases, like 4 and 5, is if you decided to just check out the two parallel planes and you want to make sure that they're not like case 5, which means they're not coincident, you could always take a point on one plane and see if it exists on the other plane. And if it doesn't, that means it's a case 4. They're actually distinct from each other. Let's talk about the solutions for a second. In this case, there are no points that exist on all three at the same time. Okay, now there could be points like here, here, and here that you're talking about that might be able to like touch two planes at once, but there's no there's no points that would be able to touch all three planes at once. Now, in case 5, you do see that there is like a line right here, okay, where all three planes are touching at the same time. And that's why your answer will be in the form of a line. Okay, so we'll see an example of that a little bit later. You still have infinite number of solutions. So lastly, I grouped 6, 7, and 8 together because in all three of these cases, when I looked at the normals, none of them were actually scalar multiples to each other, and so none of them actually have parallel planes. Okay, I'll show you what the last one looks like, and then I'll scroll back up. So this one is going to look something like that. Notice that they're not parallel to each other, and so I don't see it in my normals. Okay, these first two, 6 and 7, actually look a little bit, or rather, they're kind of more similar in terms of my process. There is something that you can do. Both of these guys are called coplanar, which means, and I know this is going to be a little bit difficult to explain, if I were to draw normal vectors for each of the planes, something like this and something like this, it's hard to show you through a video, but all three of those could potentially lie on its own plane, like its own piece of paper. And so we call that coplanar, as in like all three of those blue lines could exist on a plane. like a fourth plane, I should say. And so the way that we check to see if something is coplanar is we do the dot product of the first normal dotted with the cross product of the other two normals and seeing if it equals to 0. So these two cases, case 6 and 7, they pass the test of being coplanar, whereas case 8 does not. And so notice that we don't get it equal to 0, and therefore this one is the only one that is non-coplanar. So you can automatically eliminate 8 by even just checking the coplanarness of the cases. In all three, though, it's not necessary to do the coplanar test, because what you can do is you can actually just intersect them. So if you do substitution elimination or you use the matrices, what you can do is see through what you get, and I'll do some examples for you in this video so that you can see. Even if you don't do the coplanar test, you can do substitution and elimination of all of the planes and be able to get the solution of either, if we take a look at the first one, we don't have any solutions because none of the planes actually have points that touch all of them at the same time. Okay, we could also see an example when we do substitution elimination or we use matrices where we have infinite number of solutions. And so all three are touching at one edge, which is a line. That means that we'll have infinite number of solutions in the form of a line. And even if we didn't do that coplanar test, we could also just do substitution elimination, and that should lead us to this one where all three of them actually only touch at one place all at the same time, and that is at a point. And so we would get one unique point. And so I've been talking about theoretical. Let's actually put it to the test. Here's an example of 3 planes, and we're going to do a full analysis on how they intersect with each other. I'm actually not going to include a sketch, although, we can just refer back to the cases. Okay, so the very first thing I'm going to do is I'm going to check the normals. And again, you guys know how to find the normals, right? The 1, 2, and 3, the 2, 4, and 7, and the 2, 4, and 6. So I have that right here. Taking a look at the normals, we want to see if any of them are scalar multiples of each other, and it looks like this one doubled equals to this one. And so from this, what I can say is I can go, okay, 2 times normal 1 is normal 3. That gives us a couple different cases. So already we can eliminate some of them because it looks like normal 2 isn't a scalar multiple that's included. Okay, now where are my notes? I have the possibility of case 4 or 5 in this case. Okay, so we've narrowed down out of all 8 cases, only 2 of them now fit this situation. So the next thing I'm going to do is I'm going to compare the d values. And it looks like the d values are also doubled. Since the doubling matches the normals, I don't have a case of 4, but I do have a case of 5 then. So that was, if I go back to the diagram, this guy. Okay, so as you can see, I have 2 scalar multiple normals and the same 2 d values that are scalar multiples of each other as well. Okay, so we're looking for a line as our final answer. Okay, going back to my question now. What we're going to do now is, in order to find the intersection, we have to do substitution or elimination. In the videos, because it takes way too long to do the substitution elimination, I've opted for the matrices. Again, that's not part of your curriculum, and so in my own class, I would be teaching the substitution elimination, and this is something that my students can use if they decide to. If you want to use a substitution and elimination and you want to be taught that, I think you're going to have to be taught that in your own classes. Okay, so what I'm looking to do is take the coefficients of plane 1 and plane 2, and I want to intersect them. It doesn't matter which ones you intersect because all 3 of them will intersect at the same place, which is a line. Okay, so you just chose whichever two looked easiest, and I started to put them into row reduced echelon form. Now notice that at the very end, I'm left with 1x, 2y, no z's, equals to negative 31. So I didn't really solve for anything there. This is 1z equals to 9. Okay, that might be something useful. So I've written that right here in row 2. Okay, and because I don't have a specific number that a specific value that I've solved for in the purple, I'm just going to let y equal to a certain scalar. That's going to be the scalar, I shouldn't say, well, I can say scalar. That's going to be our parameter for our line. So I'm going to use t because we always use t for our parameters. I'm going to substitute it into my y, and I'm going to solve for my x. All right, so when I write it down as an x, y, and z, I have my x right here. I have my y, which I said was just 1t. I put that placeholder 0 there because it'll be easier to separate into my position vector. And then I have my z value. Remember we said that z was 9? And so we didn't have a t value, but again, I want to put that placeholder there because it'll come in handy when I take a look at my direction vector. All right, so that was one way that we could possibly do it. Another way is if I got that z equals to 9, and instead I didn't want to put the t value or the parameter into y, I had chosen x instead. Okay, so we could always put our parameter k or t, whatever, put it into x instead, and we would just do the exact same thing. We would just have a k as our parameter instead of the t. Okay, now as a very quick reminder, here is our x, which you replaced with the k. Here is your y right here. And then you said that z equals to 9, like you solved for it. Separating each of those into the line, so our vector form for a line, make sure that you guys do not reduce this part, but you can reduce your direction vector to make it look a little bit nicer. And so what you can do is multiply the entire thing by the lowest common denominator, which I'm seeing is 2. And so by multiplying this entire thing by 2 over 1, you'll get the direction vector that I have down here. So really, your final answer can be either of the pink formulas that we had. So I wrote one before, right? Or it can be this one. We can have many different versions of the same line. Okay, so let's take a look at two more. Here's example number 2. Obviously, it looks exactly the same. So we're going to check out our normal vector and our d value. Now, taking a look at our normal vector, it looks like, well, none of these normals are scalar multiples. And so when they're not, we have cases 6, 7, and 8. So those were the last 3 cases we had talked about earlier. When we do, say, I just wanted to see if the coplanar test even worked. We know none of the planes are parallel. And so I decided, you know what, let's just see if the coplanarness works. Okay, because if it does, we have a case of 6 or 7. If it doesn't, then we have a case of 8. Okay, so I did the dot product of the dot product of the result from the cross product. By the way, this is called the triple scalar product. So this process right here is finding the triple scalar product, which is a dot product of the cross product. Okay, and if it equals to 0, that means that they are indeed coplanar. And it does. It equals to 0, which means that we're not talking about case 8. We're actually talking about case 6 or 7. This is not a test that you absolutely have to involve because you can just jump forward into solving right away. Oh, I guess this is another way that you could say that they're coplanar if you really want to. So I'm going off of my coworker's notes, and she just wanted to give you a lot of information. This is another tool you can use. If you cross both of normal 1, normal 2, and normal 3, you should get a perpendicular vector, and if those are scalar multiples of each other, they're also coplanar. But again, you don't have to do any of these things. You don't have to check for coplanarness. All you can do, well, all you have to do is just substitute and elimination. Okay, so I did substitution and elimination through matrices. And what you're looking for at the very end when it's in row reduced echelon form is this. This will tell you if you have case 6, 7, or 8. In this case, they're saying 0z is equal to -2. Does that even make sense to you? Like, there's no values of z that could ever multiply 0 to give you -2. Automatically, I know that these guys are probably distinct. Okay, so there are no such values for z that would make that work. There's no points of intersection. There's no solution. And therefore, this guy is case number 6. Okay, so let's just remind you what that looks like. Oh, sorry. Case number 6 is the one at the top. It's the only one that has no solutions. So all three of them are distinct from each other. Let's take a look at my last example. Okay, as you can see, looks exactly the same. In fact, I could just look like example number 2, you can tell, right? Compare each of the normals and they all look like they're not scalar multiples. And so we would say they're not parallel. That's a case of 6, 7, or 8. You can check if you want to and do a coplanar test. Okay, you don't have to, but if you do and you see that it equals to 0, like the triple scalar product equals to 0, that means that it's only a case of 6 and 7, so it's not a case of 8 anymore. Doing substitution or elimination, either through substitution and elimination or matrices, so I reduced everything to row reduced echelon form. I'm sorry, I'm going pretty fast now. I take a look at the very end and I'm like, okay, did I solve for anything? And I see this, and that's actually pretty indicative of something. 0z is equal to 0. Any value that you put into x will always multiply by 0 to give you 0. And so there are infinite points of intersection. This is not a case of 6. This is now a case of 7. Okay, so we're looking at case number 7 now. And that's where we actually get a line of intersection. I'm just going to remind you again really quickly what that looks like. Okay, so here's case number 7, and we're now looking for this line of intersection. Okay, I'm just going to scroll back down. Sorry, guys. There we go, right at the end. What I would do is I would say, well, no matter what z is, because it can be anything, I'm just going to make it my parameter. And so I'm just going to say, let's take k as my parameter. We're going to sub it into the equations, the orange and the purple equations from before for our x and our y. Sub it in and start solving for your parameter, your parametrics for x and y. Those go into my equation. So here's x, right? There's my y. And then we said that you wanted z to be k. And then we're going to rewrite it in terms of vector form. We'll have k as our parameter, and that's going to be our line of infinite solutions. Wow, okay. I can't believe we made it through vectors. That's so awesome. Stay tuned for some calculus vectors. I'm so tired. It's my husband's birthday. I should probably go home. It's like really late. I guess I should talk to him today, just a little bit. Throw him a bone. All right. I will see you guys later. Have a great day.